So back up to question 13. Let's just give me a simple number to use for the size of these batteries.
3.
I like
Yeah.
3.
Big man.
3 volts. Don't die in the meantime. 3 volts. So those batteries both have a potential difference of all right. Well, some people get Emily is pretty nice. Yeah, perfect, things, right? Excited? Oh, that's excited. Nice. Those are both 3 volts. Questions, comments, concerns? In this question, I believe Dr. Knight wants us to assume there's resistance in the wire. Okay? So, well, let's look at this. I'm going to contend, and the friction in the book would agree, that each of these paths is the same length. Can we agree to that? Okay.
Yeah.
Good. So we can agree that each of the 3 possible paths here has the same length, and therefore the same resistance. Is that acceptable? Okay. So let's look at this circuit first. This is rather more complicated one. We're going to pretend that we are electrons. So put your electron hat on, Miss Frizzle style, going to med school bus. So here's an electron right here. I need a name for this electron. Carl. Carl electron is going to leave this battery. Carl wants to go from where to where? Negative to positive. Wants to go from the negative potential to the positive potential. Agreed? So he's going to have to pick one of these 2 paths. Would Carl take both paths?
No.
No, that would be silly, because then you would go like this, then around, and then you just wouldn't have. So Carl is either going to go through 0.5 or through 0.6. Carl's on the left, and then Carl goes through 0.5. Here he goes. It would be, assuming these paths are equal, yes. Right now, we'll say yes, random. Here he goes all the way around. Yay, Carl. So, Carl. What was... Very good. Carlton, what was Carlton's change in potential through that path? I need a number. What? 3 volts. Carlton went from a negative to a positive. Carlton had a change in potential or a change in energy of 3 volts in that loop. The battery made a 3 volt tall mountain, and Carl went from the bottom of the mountain to the top of the mountain. Yes, no? What's wrong with that? What'd you say? There's a chemical reaction taking place inside this battery that gives it energy. This battery is going to produce X amount of joules, and an electron will get so many joules every time it comes out of the bottom of the battery. It gets, the electron, it starts inside the battery here. The chemicals react, and it then leaves the battery with X number of joules. As it goes around the circuit, it loses those joules and goes back to the top again. As it goes through the battery, it gets re-energized with those joules, and then does that over and over again until the battery stops with the chemical reaction.
Makes sense. Got my vote.
It loses energy as it goes around the circuit. Correct. It always uses all of its energy as it goes around the circuit. Good? Or is it get closer to being good? Why volt? A volt, as we said, is, I mean, I agree. I'm going to try and say this up. Hold on to that question. 1 volt equals a joule per, if it's an answer question, let me know when I'm done. A volt is a joule per coulomb. So if I have a 3 volt battery times, we know the charge of an electron is 1.6 times 10 to the negative 19 coulombs. If I were to multiply that together, that would actually give me some number of joules. and I could actually figure out how many joules of that electron got. But the 3 volts is just a generic term they give us that would apply to any charge. It just happens only electrons move. So we could at any time compute the energy of a certain electron if we wanted. Is that what your question was? Why volts, not joules? We'll use the term volt and joule. If we're not going to do this math right here ever, we'll use volt and joule pretty much interchangeably because they're essentially the same thing. Okay. Question about Carlton. Okay. So here's another electron. Call him Will.
Will?
And to follow the Fresh Prince of Bel-Air thing here, Thomas. Work with me here. Will Smith, the star of the show, Men in Black.
No.
Okay. Will comes around. We're running out of time here. Sorry. Will comes around this circuit like this. Yay for Will. What was Will's change in potential?
Same thing.
Also 3 volts. Not like in this morning. There we go. 3 volts. So it's the same change of potential. No matter which path they take, it's the same change of potential. Can you agree to that? Awesome. All right. Now we have one more electron we're going to pretend to be.
Green. I think it is Phil, yeah.
It's Phil. It's fine. Ashley. Good. Ashley is going to go around.
I hate it.
Focus. We're going to go around this circuit over here. Yay, all around. What's Ashley's change of potential? 3 volts. You got that down here. Good. 3 volts. Now, what did we say earlier about the resistance of all 3 of those paths?
Same.
They're the same. So,
Same length.
if we believe that current equals voltage over resistance, which we do, how would the current of Ashley, Carlton, and Will compare?
Same.
They're the same. They're the same potential. They're the same potential, same resistance we just said. So the current at 3, 5, and 6 all need to be equal. You okay with that? They're the same wire, same length of wire, all those, the R equals field elevators. I'm going to assume they're all copper. There's other variables I'm going to affect. So, these 3 I'm going to each say has a current going through of X. Is that okay? The conservation of charge tells me that in this single loop, those all have the same current. So 1 has a current of X, and 2 has a current of X. That's why those are all equal. The conservation of charge tells that in a single loop circuit, if there's 2 coulombs per second here, there has to be 2 coulombs every second here, and then 2 coulombs every second there. It's the same current in all places. So 1, 2, 3, 5, and 6 are all equal. Question. If you agree with that, you math with the data. Why with? Okay, let's back up. Let's do this first. 3, 5, and 6 are equal. Anyone need to be convinced of that? Okay, that's good. In a single loop circuit, the current is equal in all places. Another example might be, think about the chain on a bicycle. The chain is moving the same speed the entire time. It doesn't go faster before the sprocket from the back wheel or after. It's one speed all the way while you're pedaling your bike on the chain. Same thing in a single loop circuit. Electrons all move at the same continuous rate. Now, 4, what's 4 going to be? What's spot 4 going to be? If this is all true, what do we know about spot 4? Double. I would say 4 is going to be 2x, because if I have 2 coulombs per second going this way, 2 coulombs per second going that way, it should be 4 coulombs per second.
The 4 is where they meet up.
Correct. And then the 7 would be the same argument for that right before they split. So the same battery can produce different currents in different circuits. Okay, what's that? Whatever.